morning everyone. Thank you for the opportunity to speak to you today. And a particular thanks to Diabetes SA for organising this session, and very recently for giving us a little bit of research funds to get a little bit behind the research I'm going to talk to you today. So I guess a lot of us know what this space looks like and feels like, probably to work in for some, or they're aware of it. It really is an incredible concentration of institutes, flagship universities and the new Royal Adelaide Hospital. It's a terrific place to be doing medical research, and it really kicks well above its weight for research in Australia. And this model here also includes a picture of the new SAHMRI 2 building that's going to be located in between the university and SAHMRI. This is going to house a proton therapy centre, which you've probably heard a little bit of press about. The newest models of that actually have that building about the same height as the University of Adelaide building here, about twice the current height, but in the same footprint. So it'll just, again, add to what we can do here in Adelaide, which is really something to celebrate. I'm affiliated with two main groups, the University of Adelaide. I'm a staff member and professor there. And we do work with the Centre of Research Excellence in Nutrition. So this is a group of people that are very interested in how nutrition and a gut-centric approach to health can benefit the community from the very building blocks of research. So these guys are looking at people who are diabetic, obese, the critically ill, the aged populations, to try and bring out better nutrition with a gut focus. So my team is part of that bigger group, but I'm actually physically located within the SAHMRI building, within the nutrition and metabolism theme. So my group is a basic science group that do have the privilege of working with clinical researchers as well to translate what we do in basic science to understand more molecular processes that drive some of our health problems in clinical space as well. And for those that haven't had an opportunity to come along and visit SAHMRI, I would really encourage you to do this. This really is a flagship medical research institute. It has some stunning architecture, and there are tours that you can hook onto that occur twice on every Friday. And I encourage you, if you're at all interested, we'd love to see you there to take part in that. This is a product of the government, a lot of collaborations. It's there for the community. It's bright, open glass. It's there to be a flagship for everyone to enjoy and to feel connected with. So please take that opportunity if you can. So, as I've mentioned, I'm going to be talking a little bit about the gut. And apart from the nutritionists here, it's not always the first point that people think about when they think about diabetes control and metabolic health. But I'm hoping by the end of this talk, I can convince you that we actually probably should have a closer look at the gut and give it a little bit more thought when we think about overall health. I'll talk about sweet taste and how the gut can also participate in sweet taste. Talk about whether this changes in type 2 diabetes. Talk about some of the studies of disease origins around the use of sweeteners in this space and how that may affect the gut. And then I'll finish with a clinical trial we've just done with artificial sweeteners in people that are healthy. And finally, just to flag an opportunity too, that you guys can be involved in the research we do by promoting it amongst the patients that you see as well, to try and help us recruit into these studies. So I guess the reason we're here is because type 2 diabetes still remains a global epidemic. These numbers keep getting scarier. 415 people currently, according to World Health, currently have type 2 diabetes in particular. 1 in 10 people, or 642 million people by 2040 are projected to have a need for the care that you guys offer in the community and we do in research. So there's clearly a need for us all to work harder and smarter to find better ways to manage this condition. And of all the people, you guys in this room know most about this slide, what determines overall blood sugar levels. None will be surprising to you. Physical activity, medications, illness, stress, dehydration, menstruation and pregnancy. But often we don't think quite as much about meal-related blood pressure. These are things like meal composition, the amount of food we eat, when we eat, the health of our kidney and livers. And in particular, things that the gastrointestinal tract plays a direct role is in the delivery of nutrients into the absorptive part of the GI tract. So when nutrients first actually become available to be taken up into the body, their digestion and absorption, and in response, the release of insulin. And the gut plays a very important part in providing hormones that almost double insulin output. So the gut plays a very central role in this. And so our research really is focused in this space to try and make people more aware of how important the gut can be. Most diabetologists have traditionally thought of type 2 diabetes as a problem of excessive glucose in the circulation, which is certainly very true. But one of the very first port of entries that sugar has to get through is to be taken up through the wall of the gut and being presented to the circulation. And I think we've overlooked some of the opportunities in that space to control blood sugar. It's a bit like you're dealing with the bull in the china shop, but no one's actually stopped and said, why don't we close the door of the china shop? This is where our research really is focused in on, what the gut wall can do in terms of closing that or making it harder or slower for that entry. The reason why the gut's so important in the research we do is because it participates for so much of the day in how we control blood sugar in the body. So most of us will be having 3 meals a day, and that's indicated in the red period here, where food is within the gastrointestinal tract. And you can see that these tend to overlap quite a bit for most people. And then the gut's also playing a role in the post-absorptive state by providing hormones that support insulin production and therefore glucose disposal in the body. So the only true time that the gut probably isn't playing a role in overall blood sugar is on your fasting blood sugar measures. And you can see for most people that in yellow, that only occupies a pretty small part of the day. So the gut potentially is quite important for the vast duration of our time because most of us spend limited time in this fasting state. Now, I don't know how good your memory is of Physiology 101 when you did the gut section, but I'm just going to give you a quick run why the gut is an incredibly sexy organ and you should pay a lot more attention to it. I'll let you know, you can let me know at the end whether I convinced you. So, first of all, the gut is a sensory organ. The gut is 9 metres in length. It has a surface area because of specialisations in the endings here to create villi. It has a surface area about equivalent of a tennis court. So this is the surface that your body can absorb nutrients across. It produces over 35 different hormones, and this is more than any other organ in the body, which is quite incredible. And many of the new diabetic medications are actually mimics of some of these gut hormones that are produced in response to the ingestion of carbohydrates. It has its own nervous system as well, the enteric nervous system, which operates both independently and also connects to both the sympathetic and parasympathetic nervous system. So this is an incredibly complex picture. I don't expect you to take much down from this other fact that this system has mechanical and chemical sensors capability. It's involved in propelling food down the gut. It's important in generating pain signals and overall control of digestion. As I mentioned, it also contains a great deal of neurochemicals as well. The gut also has its own immune cells. We often don't think the food we eat hasn't really entered our body, but it hasn't really entered our body until it's been absorbed. So the gut actually has a surveillance system that's uniquely tuned to the needs of the gut. And there are gut-specific immune populations that do surveillance on all the food we eat and are important in generating some inflammatory responses that are then projected to the rest of the body. And it's also home to over 100 trillion bacteria. Now, I don't know who's actually counted them all, but these are more than the human cells we have. If we were ever taken by an alien race and probed, they'd say we were bacterial. And the way these are hosted in the body and their effects on our overall health, we're only just starting to understand, but it's going to be a new frontier in the way we do treat patients into the future. And I will talk about that later on. As I've mentioned, the gut can also sense. Anyone who's had patients that have gut pain know that the gut is particularly tuned to sensory and physical pain. And there's an extensive network of both the sympathetic and parasympathetic nervous inputs to the brain that control that. And also there are chemical sensors that are hooked into this as well. This is an example of a taste cell, and this is a cell within the gut that also has similar capability, and I'll certainly be talking more about that. So not only can the gut, it can smell, it has receptors that we have in our nose, an olfactory system, it can taste with the same receptors we have in our tongue, and it can convey all these signals as neural signals to the brain and also as gut hormone outputs. So pretty cool, huh? Good starting point. We should be doing more about this. Let's talk about what happens during a regular meal. So when food empties from our stomach, it interacts with sensors that are located within the gut wall, very much in the proximal portion of the gut. And that can release a number of gut hormones, and the ones that are important for carbohydrate management are the incretin hormones, glucose-dependent insulin-trophic peptide, or GIP, and glucagon-like peptide 1. So these are the incretin hormones that act on the pancreas to effectively double insulin secretion. And this is where the current generation of diabetic medications are mimicking this action with drugs like Zenotide, or Byetta, as you may know it, and liraglutide, which is Victoza, which probably you've seen quite a lot in the community as new generation drugs. So they mimic the action of these two hormones. These hormones themselves can also slow gastric emptying. They provide feedback that ultimately results in parasympathetic reflex control of the stomach and slows the subsequent emptying. So it gives people a sense of early meal termination as well. So it can also be effective in weight loss, and it's just been approved by the FDA. Zenotide has been approved by the FDA as a standalone weight management control drug. The first one that really doesn't target the brain specifically, it targets this pathway. In addition, sugars are brought into our circulation through this process of glucose transport, and that in itself leads to feelings of fullness and satiation. So when we first started this research, there wasn't a great deal known about really how we do detect sweet and the mechanisms that the gut use. So we, of course, turned to something that we all enjoy, and one of life's great pleasures from time to time is tasting something sweet, whether your thing is boiled lollies or whether it's the creme brulee, it's up to you, but most people enjoy sweet. And it came on the back of a whole lot of research that had recently de-orphaned a lot of receptors involved in the chemical transduction of these nutrients into signals in the body. And this was a lot of research that was done around receptors in the tongue. And you can see that we now know the structures that respond to umami, which is your meaty MSG Vegemite taste, sweet, bitter, sodium, sour and carbonation. We now know about 3 or 4 others, particularly around the detection of fats. So we know now what the actual molecules that detect these are. For sweet, this is a very complex receptor, but this is one receptor complex that recognises everything we know as sweet. Unlike the bitter family, where there's upwards of 40 different receptors, there is just one receptor in our body that allows us to detect sweet taste. Whether this is sugars, sweeteners, some sweet amino acids, or sweet proteins. And for those that are a little bit more scientifically minded, this is what the receptor looks like in 3D space. It actually forms a Venus flytrap receptor and has multiple binding sites. So you can have sugars occupying the top space. You can have also some small molecular sweeteners combined in this hinge region and also within the transmembrane domain as well. And that's often one of the strategies that Big Sugar uses in their artificially sweetened drinks, to use combinations of sweeteners so they can both bind at the one receptor and increase the mouthfeel without introducing some of the bitter or high concentration effects that you sometimes had with earlier generation sweeteners. So it's very complex, but it is the receptor that conveys sweet in the body. So this is how it works in the tongue. We have this receptor located within a taste cell, within a taste pore here, and when we eat something sweet, this triggers the activation of this receptor, signals through a signalling pathway, there's an exchange of ions, and ultimately it signals to the brain via our sensory nerves, the corda tympani and the glossopharyngeal primarily. And we can map some of this in the brain. This is some positron topography images of where the brain perceives different tastes. You can see that they're also coded for region as well in the insular cortex in the brain. That's fairly recent knowledge as well, so taste is coded in the brain as well, where it's received. The way we have looked at this by looking at the gut is to access the gut via endoscopy. So we're very lucky to be involved with folks from the Royal Adelaide Hospital gastroenterology department, and we're able to do research endoscopy in volunteers that come along to our studies, where we pass an endoscope down into the duodenum and we can collect tissue samples using small biopsies. Here, this is painless. These biopsies usually are under 5 milligrams. They're tiny pieces of tissue, but we can do a great deal with them in terms of understanding how this system works. And we were one of the earlier groups to show that not only does the tongue have this unique capacity, but also the gut does as well to detect sweet taste. So this is some immunolabeling. So this is using antibodies that detect sweet taste receptors and then fluoresce red where they're located in the cell. So this is a cross-section of one of these biopsies, and you can see that this receptor here is expressed on this particular cell, and it also is a cell that makes this incretin hormone I was talking about earlier, glucagon-like peptide 1. So for some people, the concept that the gut tastes sweet is quite foreign, so I need to get you over that little hurdle, because it does. It isn't connected to our conscious brain in the same way, of course, because that would just be unpleasant. But it does play very important roles in how we control sugars. Now, while I've shown you that in humans the evidence is that there are this receptor system is present in cells that can release hormones, animal evidence is very strong that that's the case, but there's mixed evidence in humans whether that actually relates to function. There's studies that show that sweetness, for example, can trigger some of these hormones. There's other studies that show that it can't. So clearly they may be involved, but they may not be relevant in all circumstances in terms of levels getting into the circulation. However, we've taken some of these little tissues off the biopsy forceps and kept them healthy and happy outside the body and stimulated them with sweeteners ourselves very recently to see whether the tissue itself can produce, so to get closer to the source. And we've been able to show in these biopsies from the human duodenum that indeed if you trigger them with artificial sweeteners in an escalating dose, you can get this tissue outside the body to dump this hormone into the test solution. So it appears that the human tissue itself can produce this hormone, but whether it can produce significant levels to get to circulation, we're not sure. This hormone, however, may have very important local effects on sugar transport. Now, sugar transport trucks look very bad. This is the best one I could find, this is back from the 60s. I'm going to use this as to indicate sugar transport over the next few slides. So, Physiology 101 on glucose uptake. In the gut wall, there's two main transporters involved. There's a sodium dependent transporter up here. So this is where our food is coming through. And this basically vacuums carbohydrates and glucose out of our food into the cell. And it requires energy. And then this transporter here, GLUT2, sits on the basolateral surface of your enterocytes lining the gut wall and delivers sugar into the circulation here. So this is the gate that I mentioned earlier that sugar has to get through in order to be presented to the circulation. So some very elegant studies done in animals from the Mogolsky lab at Mount Sinai in New York had a look at how mice that lack these sweet taste receptors might respond to sugar transport. So these were mice that had the sweet taste receptors genetically deleted, and then they put these mice on a high carbohydrate diet. Now, in control mice, if you give them a high carbohydrate diet, what you can do is increase levels of glucose transport. So there's more expression, there's more protein, and there's more rapid sugar entry through this pathway. But if the mice that lack this sweet taste receptor, the transport wasn't changed. So it's very strong evidence that the sweet taste receptors are one of the gate opening mechanisms for sugar transport in these animals. I thought, well, that's pretty cool. Why don't we have a look and see what sweeteners do? So they did the same thing here. So they kept the animal this time on a low carbohydrate diet, but they supplemented it with artificial sweeteners. They used sucralose in this study. And they found exactly the same thing, that artificial sweeteners could interact with this receptor and cause sugar transport to be exaggerated in control mice and not changed in animals that didn't have this opening mechanism. So pretty strong evidence that this is the way sugars in our diet are recognised and in response effective transport. And you can imagine this would make sense. If we were having a lot of sugar, humans use sugars as the fuel source for the brain, so it's a high priority substrate for the energy needs of our body. So we're very tuned to bringing them in. So this is the lock and gate mechanism that occurs by. So we've built up a model of this system that looks a little bit like this. We have Amongst the absorptive cells in our body, we have specialised cells that are equipped with sweet taste that, in the presence of glucose and potentially also in the presence of artificial sweeteners, we can activate these transporters to both absorb sugars and also potentially release gut hormones. So that's terrific. It's good to know from previous literature what that means. The main point of this one is here ahead of you. What we wanted to know a little bit more about is this system disrupted in people who have type 2 diabetes, which is a very important question to ask. So really, is this system changed by glucose in the diet, or is it glucose in the blood that changes it? And is this different in type 2 diabetes? So I'm going to summarise a whole lot of research in only a couple of slides here. We did a clinical study where we brought in both diabetic and non-diabetic subjects into this clinical research. They attended over 2 visits. On one visit, we clamped their blood glucose levels at fasting levels, and on the second visit, we clamped it at 12 millimoles at the post-meal blood levels. So we were seeing whether the influence of changing the blood glucose level could affect this system. And in both those days, we then infused glucose into their upper gut. We then collected biopsies and had a look at how this system was changed under those conditions. And what we found is that in people that were non-diabetic, on the normal blood glucose day, when glucose was presented to them, this system increased. And this probably makes sense, because if this is a system that's important in bringing sugar into the body, you'd want it to be responding positively to control glucose entry. However, when they were at high blood glucose, we found the system did the opposite. It actually shut down. So this, we believe, is a switch that protects blood sugars overshooting when its blood sugars are already high in the body. So it's basically a safety switch to prevent excessive transport of sugars and adding to an already high circulating blood glucose level. However, what we found was that people that had type 2 diabetes couldn't turn the switch the other way. So people who had type 2 diabetes, who we already know tend to absorb more sugar from their diet, we found that this system wasn't modified in the face of a high blood glucose, so potentially exposing these patients to excessive uptake. And when we looked at that, we actually found that that was the case. So we used a marker for absorption called 3-O-methyl-glucose, which enters as glucose does but isn't metabolised. And we showed that the diabetic groups at high blood sugar definitely had a significant increase in the amount of glucose they were bringing into the body. So potentially this system is one of the important gating mechanisms, and it appears to be different in people that have type 2 diabetes. So what's the benefit for us in understanding this system? It's that this potentially is a system that we could target in a new way to look at blood sugar control in the diabetic population. So if we can target this receptor and potentially reduce its downstream effects, it's a new way of looking at diabetes. Rather than dealing with glucose disposal in the body, it's one of looking at and modifying the way that glucose enters the body in the first place. It's only to slow it, it wouldn't be to stop it, of course. But the drugs in this class would not have to be absorbed into the body, so they'd have a very high safety margin. They could operate only within the gut wall, exert this effect, and not actually be absorbed themselves. So that has a high safety margin as well. So we're actually running a clinical trial in this space at the moment, looking at blocking this sweet taste system with a food-grade ingredient called lactazole, which is used a little bit more in the States than it is here, and it's used actually in products to reduce the intense natural sweetness of it. So we're trialling that at the moment in a clinical trial. And Nicole's here, and we've got a set of flyers, and we're hoping at the end, I'll mention it again, but it's a great opportunity for you to get out to the people you see on a daily basis and perhaps get them excited about this potential and being involved in the research. Okay, sweeteners. I haven't mentioned sweeteners, so this is important. Let's talk a little bit about artificial sweeteners. They are, of course, very pervasive in our food chain, and these are some of the lead candidates. Sometimes they're not known by their name here, they're known by their E-code, and some of them have very long histories back to saccharin that was found at Johns Hopkins back in 1879 as a coal tar derivative. But as I said, they're very pervasive. Probably most of us know the mass distribution of these came when tab was first introduced to the population back in the early 60s. That originally contained cyclamate, and then it was moved over to saccharin when the FDA lifted the approval for cyclamate in the US. This is a big industry though. It's expected to reach 2.2 billion by 2020. It's growing at about 5% a year. So there's a big exposure of these ingredients in our food chain. And this is a little bit dated, and I apologise for that. But it shows that really it's only been fairly recently that these have been available in the food chain. Of course, there's been an exponential growth in the number of products that contain it. They're increasingly marketed to the health conscious. Artificial sweeteners and health is perhaps not such a clear story. There's supportive evidence that they're healthy. There's a big footprint of the food industry in that space. And there's trials that suggest we should look a little bit closer. I'm going to present a little bit of that. This is perhaps the bookend of the two. One of them is the marketing. Of course, the marketing suggests we shouldn't have any regrets and they're healthy and we should enjoy it as a part of a balanced life. This is the marketing angle. And then you get those that are very health conscious and would like to point out all the studies that have shown negative results in this space about how artificial sweeteners could impact health, things about changing the way the brain recognises sweet cues, things about turning on fat storage because sweet taste receptors are also expressed on fat cells, adipocytes, and also the effect that some of the ingredients can cause addiction. Probably between the two is the truth. But research has to fill that space and knowledge has to fill that space. One of the ways that's been done in the past to look at disease risk is to use studies of disease origins or epidemiology. This is a group of studies that have done a meta-analysis on a series of clinical trials. These were just looking at food diaries and seeing whether a certain intake pattern was linked to the incidence of the disease. Now, some of these have very large numbers of individuals and some of them extend back over 40 years. They're a blunt tool, but they're a helpful tool. So what this shows is this solid blue line here at 1 is no risk, and everything to the left is less risk, and everything to the right is more risk. So this is the risk of developing type 2 diabetes in the community based on the intake patterns of sugar-sweetened beverages, first of all. This modelling is raw here, and it's adjusted for body weight. One of the criticisms of this field is that people who tend to be diet conscious are more likely to consume sweeteners, and they may have pre-existing clinical reasons why they may be more at risk. But when we look at the study data around artificial sweeteners, you see it's actually very similar. The trial data suggests that there is indeed a rightward shift in people who are consuming artificial sweeteners, particularly those at excessive rates. This type of information is driving conversation around sugar taxes globally, and many provinces are starting to take notice of this and implement sugar taxes. And Mexico, which was one of the first provinces to start it, is already starting to see health benefits from that. But the question is, why have we pretty much ignored this? And the reality is we don't have enough quality science in this space, so this is where we're trying to work. But what this data does say, it's association data, it's not causal data. It does say that switching someone from a high intake of drinks sweetened with sugar to one that is sweetened with sweeteners doesn't reduce their risk of developing type 2 diabetes if their same intake patterns are maintained. So it's not the panacea that many might think. There's evidence that high intake of sweeteners has been associated with changes in glycated hemoglobin as well in healthy non-diabetic adults, independent of body weight as well. There's also some evidence that in some populations, artificial sweeteners prior to an oral glucose tolerance test can increase blood glucose over several hours. This was an obese diabetic population. It may not be true for all, but this was a quality study. And as I've mentioned, this is the main problem facing the field. This is why we're trying to work in this space. Interestingly, none of these studies have looked at glucose uptake. None of these studies have looked at glucose combinations. They're often the most common way we see sweeteners in our food chain is in partners. There's usually two because of that sweet taste effect I mentioned earlier, but no, they've never been tested in combination. So we recently did a clinical trial to ask whether sweeteners affected glucose absorption and whether this worsened blood sugar control. It was a proof of concept study, so it's not a large clinical trial, but we looked at two different interventions, one where we had patients consuming capsules that contained either a placebo, which was cellulose, or a sweetener combination that's very common in a lot of retail beverages, sucralose and acesulfame K. It was in capsules, and they were equally weighted so that they didn't know what they were getting. They weren't released in the stomach, they were released in the upper portion of the gut. So that's the first time the sweeteners were exposed to the body. This is equivalent in dose to about 400 mils of drink per capsule, and they consume three of these a day. So about 1.2 to 1.5 litres. So this is pushing it, but there are people that put these sort of volumes away on a daily basis. So it's high, but it's physiological. These people had this treatment. We went in and measured the state of their sweet taste system via endoscopic evaluation and infusion before the study and also after the study. So I'm going to show you, okay, there was a white background on that, so you'll have to bear with me. This is some of the research data. So I've got 3 or so slides of research data, so I'm just flagging that. You can go to sleep and look at the summary boxes at the end if you want. I apologise, this is really hard to see, but what we did in these patients is had a look at how glucose was entering the body. So this is the appearance of this glucose analogue in the circulation after we delivered it via the gut. And you can see, I hope, that patients who were on the placebo treatment were here, and patients that took the sweetener over 2 weeks were here. And there was a 20% increase in glucose absorption over 2 weeks. This is clinically significant. This is the same amount of glucose absorption shift you would normally see with metformin in the opposite direction. So we were really quite surprised to see this. So this is more rapid entry of glucose to the body. I do apologise these haven't come out with the white background, but this is the blood sugar profile, and this is, I'll trace the placebo group here in black. So this is a pretty standard oral glucose tolerance test type profile, and what we found in patients that had had the sweetener, there was a higher peak at a longer period that they were in relative hypoglycemia compared to the people in the placebo arm. This is a 24% increase in blood glucose area under the curve in 2 weeks. So it's disrupted controls of blood sugar levels in otherwise healthy people. We also had a look at this hormone I mentioned, GLP-1. This, of course, is important because it augments the insulin outputs. And what we found in these patients was that the placebo are in black here, and the patients that had taken the sweetener had lower levels, 34% decrease in this hormone. It's really important in disposing of glucose in the body. This is probably because more of it was absorbed quicker in upper portions of the gut, so the signals that normally get to these cells to release this hormone in a balanced way with caloric value, they didn't see as much of the signal to release. And so finally, I'd just like to run off very quickly a little bit on this study. We also looked at how artificial sweeteners can impact on gut bacteria. So we increasingly appreciate that, as I mentioned, that gut bacteria are important determinants of our overall health on a day-to-day basis, but also the determinants of chronic disease risk as well. And we've only just tipped our toe into the water with this, but it's clearly going to be very important into the future. In our study, we took stool samples before and after this study, and what we found is that artificial sweeteners, over a period of 2 weeks, increased gut pathogens that were normally absent in health. So there was an increase in 10 opportunistic pathogens and a decrease in 1 health-associated bacterium here, the cylindroid stain. When we had a look at the modelling of this relative to what was going on in the host, we found that some of these shifts could almost entirely predict what was happening in the host. So not only are there potential effects that are being mediated through glucose entry to the body, it looks like artificial sweeteners may also have consequences for gut bacteria, and that they themselves may be another avenue that the host's control of blood sugar can be affected as well. So we're in the very early days of that study, but we're very keen to look at the causality of that and to hopefully mine down into what bacteria are very important in maintaining a healthy blood sugar control. As I mentioned, and you guys have probably seen this in motivational talks, but what it means is there's a lot to go. We need to know a lot more in this space, and we're really well equipped here in Adelaide to ask some of those very important first questions. So the take-home messages here are the gut can detect sweet and in turn control glucose entry to the body. This differs in people that have type 2 diabetes and may form the basis of new medications into the future that target that entry mechanism. And as I said, we've got a clinical study underway. to look into that. At this stage, our evidence says that habitual high intake of sweeteners increases this glucose entry and may pose a challenge to maintaining blood glucose in a healthy range. And while it's too early to offer advice to the public around this, I think people who are excessive consumers of artificial sweeteners, even at this early stage, I think there potentially would be benefits to them if they did have a closer look at that intake behaviour, just as if it was sugar. So where we are in the development, as I said, we're running clinical trials at the moment with the sweet taste receptor focus and blocking this to see if we can bring about benefit right now for people with type 2 diabetes. And our work on gut bacteria is still in the discovery stage, but we're very excited where that could go as well. In fact, that could bring medications that are focused on pre and probiotic support for individuals that have chronic diseases like type 2 diabetes. Okay, this is when I get to do the promotion. So you guys are an important part of this equation for us. One of the big challenges we have is recruiting people to our trials. And sometimes you can understand that. There's an opportunity to be involved and to get the message out to the people that you see. Nicole's here and she's got a whole series of flyers. There's 10 of these in an envelope that sort of gives us some very simple entry points about how to get involved in the research. So if you guys could take one of those up and perhaps give it to people you think might have a mind to be involved in this really world-class research coming out of Adelaide, we think it's important and hopefully you guys do as well and you can support us in that as well. And I really just want to mention the 2 contact points for us. You'll find these in your documents as well, but Nicole's down here. We're at SAHMRI. We also have a central email address here that people can get us in contact. But really want to thank these guys that have backed what we're doing. They got excited about us and they're supporting our research as well. Most recently, Diabetes SA. And so it's very, with many thanks that we have Diabetes in South Australia involved in the research. Thank you guys for your attention and thank you for your time.